Hello. Today we are going to talk about memory allocation and what we think every programmer should know. In particular, we'll be talking about our experiences and lessons learned using general purpose allocators such as malloc over the last 15 years, designing custom ones, and talking about the memory management bugs we help fix. So I'm Sami Al-Bahra, co-founder of a company called Backtrace, where we build debugging technology. But beyond that, most of my career has been performance and reliability at various places and in academia as part of the George Washington University High Performance Computing Laboratory. With me are Hannes and Paul.
Hello, I'm Hannes. I'm working with Sami on the debugging toolchain at Backtrace. I have a lot of background in networking, where I previously worked on the Linux kernel stack, and basically otherwise switched around between languages quite a lot in the past time.
Hi, and I'm Paul Khuong. I used to work at Google and at Nexus. Now I work somewhere else. And in my spare time, I also hack on Steelbag Common Lisp. I'm actually a Lisper, and on concurrency kit, and that's how I met Sami. All right. So I think one thing that's very important as we enter this talk is why does this matter? One might think we've been allocating memory dynamically for, 60 years now. This should be a solved problem. Turns out it's not, and just switching your memory allocator for, say, this example, MySQL 5, shows that you can have very different scaling and performance characteristics for different memory allocator for the exact same code. And this is a hard problem because memory allocation is a very multidimensional problem, as we will see. So there's always trade-off, and there's no one best solution here. All right. So the general interface for our memory allocator will be malloc or free on POSIX, or on Windows, it's heap alloc and heap free. I think what's important to see here is that the only thing we can do is we pass a size, you get a pointer, you do whatever you want with it. There's no more information. And then at some point, you're done working with that data, and you pass it back to the allocator. And given this, I would say, anemic interface, the memory allocator is in charge of tracking what memory is currently available, what is in use, and so that when you make an allocation request, it can go back and satisfy it without asking the OS for more memory. Has to make sure that it lays out your objects efficiently in memory so that you don't run into performance defects either in your hardware or in your operating system. And it is not allowed to move objects around. Once you get an address from malloc or heap alloc, it's there until you free it. You're kind of stuck with that decision, and that's what makes it, at its core, a hard problem. Also, very important, if you mess it up, there's no guarantees here. All right, so Sami, let's go.
So this is it's actually a really hard problem. The interface is simple, but there are a lot of challenges in building a general purpose memory allocator. So let's go into a little bit more detail as to some of those challenges. One of the biggest problems is memory utilization. Your memory allocator needs to ensure that you are not wasting memory. And one of the biggest issues in memory allocators is fragmentation. Over time, blocks of memory are either too small or too large for the allocation requests made by the program. And generally speaking, there are two types of fragmentation that we care about. One is external fragmentation. So you have blocks of memory available, but they're too small for the sizes requested. So in the diagram here, every block, for example, could represent a page of memory. That's the smallest granularity in which your memory allocator can request memory from the kernel. And the blocks in red are unavailable. So in the third row, it's a downside to split screen. Oh, look. So in the third row here, for example, these blocks are available. And an incoming request comes for 3 contiguous blocks. That cannot be fulfilled because there aren't 3 contiguous blocks available. So then it would have to go back to the operating system to request more memory. The other kind is internal fragmentation. So the allocated blocks are too large for the allocation request. So imagine you have all these available blocks, you end up requesting 3 8-byte allocations, and you end up taking a page for each allocation. So in this example, you have a lot of internal fragmentation, a lot of wasted memory. The other challenge is the allocator itself needs efficient data structures to be able to quickly determine which blocks of memory are available or in use. And if those data structures are overly heavyweight, they can contribute to internal fragmentation significantly. So a very naive memory allocator may, for example, just have a simple fat linked list, intrusive linked list of all available chunks in memory. Imagine the linkage of this intrusive linked list is something like 8 bytes or 16 bytes. In this situation, you're talking about for every 8-byte or 16-byte allocation, you have 16 bytes of wastage on linkage, and that could be fairly significant. So the memory allocator does have to take this into account with respect to the data structures used internally. The other key design decision that a memory allocator has to make is decisions around placement policy. So how should it, which blocks of memory should actually be utilized for any incoming requests? So similarly here, we have these available blocks. We have some incoming requests for, A bytes of memory, B bytes of memory, and C bytes of memory. Your allocator can choose, many different options with respect to which blocks of memory end up being utilized for these requests. This can have pretty serious implications on performance for your program. And it can wildly vary between memory allocators. We have a very simple program here, pretty bare bones, where we allocate space for 3 strings and then print them using printf. And you can see within popular allocators today, there's a good amount of variance. So you have A, which is Paul, B, Hannes, C, me. And you could see that the different allocators will place these on different cache lines, different pages, et cetera, et cetera. And as you'll see later in the presentation, this actually can have significant implications for real-world workloads. The sad reality is there is no perfect placement policy. You're always going to have an adversarial workload which will break the placement policy. And this is something that allocators have to live with. So there isn't one allocator that's the best for every single workload out there. Now, a lot of these issues around fragmentation are made easier if you could actually move objects around. The biggest challenge in C++ is these addresses have to be stable. People will play things like pointer encoding tricks, et cetera, et cetera. Up until recently, people thought this was impractical. If you look at the literature, everybody's like, oh, compaction would be great, but it's not an option. Well, it is an option, and it is practical. If you're interested, Emery Berger, who's prolific in the area of memory allocator research, is giving a talk at CppCon this Thursday, and you can learn more. The graph here displays the impact of fragmentation with Firefox. Over here, you're running Mesh, which is a compacting memory allocator, and the red is default JE malloc memory allocator. So Firefox switched from system allocator to JE malloc. That's a 20% reduction in memory. And then we see another 16% or so reduction switching to Mesh. The other big challenge is multi-core. So as multi-core became ubiquitous, both the placement policies and all of the support mechanisms backing them required major design revisions.
Thank you. So the first issue was standard scaling issues as we went from a single-threaded memory allocator to a memory allocator that had to be thread safe. So if we go back to the very beginning of libc, all they did was slap a big lock in front of it. So I recreated that setup on a recent computer, and what we see is that for each malloc free pair, if you have 2 threads constantly allocating and freeing memory, one allocation, one free takes roughly 50 nanoseconds. If we re-enable the thread caching mode, that is now standard in libc malloc, that goes down by 2/3 to 17 nanoseconds per allocation free pair. So given this data, you might say, well, just move everything to be per thread. It's going to be much faster. And yes, it's true, right? If you essentially eliminate contention by giving each thread its own private heap, it's going to be fast, but it's going to be very wasteful in memory because you can't recycle memory from one thread to the other. So we kind of have to look for a happy medium. And there are 2 options here. With pt-malloc or older libc malloc, we just had a small fixed bounded size cache in front of what is still a global heap. And then more recent allocators tend to go for multiple subheaps, but a fixed number of them, and then you multiplex threads. The goal here is just to not eliminate, but greatly reduce contention. More interestingly to me, I think, is that the memory placement also becomes a harder problem because there's a bunch of sharing issues at all sorts of level of memory hierarchy. We get false sharing in a cache line, but we also even have a similar effect if it's just read-only data that it has to figure out that there's the L3 cache is still valid. Then we have something else with when you share data on multiple threads on the same page, and finally with NUMA placement. And we will touch on that later. All right, and here's a new impact, which I don't think I've seen described a lot or ever in the literature. When you map memory or you grab more physical memory from the kernel, that tends to be fairly fast, right? It's constant, doesn't really matter how many threads are running. However, when you unmap it, what we observe is that as you run the same process with more threads, either on more cores or even fewer cores, but more sockets, this unmapping operation becomes much slower. And that's not just for unmapping, it's also just what should be faster release, like madvise free or don't need syscalls. So what does it mean for us? Well, as we increase the number of cores on our servers, like say we have 128 hardware threads on one socket with AMD EPYC 2 now, well, you expect the allocation rate to scale roughly with a core count. That's why we want more threads. But then at a steady state, that means the allocation rate will also scale with a core count. And we just saw that large enough the allocations individually scale linearly with the core count. So to me, this feels like as we increase the number of hardware threads in our machines, we can expect to hit new quadratic scaling bottlenecks that were, until now, never an issue. All right.
So at this point, we probably should point out that validation is hard. So whatever you basically do and how you try to validate your assumptions about like malloc performance in a particular setting, for example, a production workload, it is like probably never really going to work out that you can simulate or reproduce it, like, for example, on other hardware, in other settings, with other configurations. So you basically always have to end up trying to test in production, or like at least as close in production as possible. So I can name some examples where this happens particularly badly is, for example, most of the common production allocators tune themselves by the given of CPU numbers. So as soon as you increase like the number of CPUs, you get different results. Also nowadays, it very much depends on how you, for example, read the number of CPUs, because sometimes in containers can actually limit the number of CPUs you actually use. So if you're suddenly in a container and your container uses a different or wrong way to read the number of CPUs, you probably like overestimate a lot of like settings in your allocation. Other settings also play a big role, like for example, optimizations that the compiler does, the version of the operating system, etc., etc. Another thing I guess I need to point out here, because I was probably selected as a more like security person here, is that in general, like we have memory management bugs in all code, and we somehow need to cope with them. And so nowadays it becomes more important that we actually are able to at least like limit the effects that memory management errors have on us, and don't give attackers like more tools, don't give attackers more tools to actually be able to exploit them. I have here, for example, one example where like a few years ago it was possible by a 1 byte overflow to actually like have a local root exploit, where some application that was set UID root was able to execute code under the attacker's control. And the basic problem, what you'd see, for example, here, which is the metadata layout of glibc, one of the most like used memory allocators, is that you basically intermix the metadata of the allocations along with the allocation itself. And so if you have an overflow behind like allocation 1, for example, or allocation 2, you basically hit or can overwrite data, which is part of the metadata header of the next allocation. And given that memory allocators are quite complex nowadays, and you actually have, for example, in the case of the free chunk, a lot of fields that you can write to, you could actually create a lot of havoc. And depending on like how you lay out your fields, it was possible to actually like run code because of this particular problem. The problem here is that basically to validate your heap, you need to like have a consistent view, but this is like not going well with the performance people who try to separate the heaps to make it faster, for example, in terms of to not destroy caching behavior. You basically can see a diagram which doesn't really point out what I tried to say. The more security guarantees you try to give, the more, in this case, memory footprint, for example, you actually have to do. This is, for example, like other canaries or guard pages need to be inserted. Slim guard probably is not like a really used one allocator, so it's hard to say if it actually like achieves the goal of like low memory footprint, low performance, high performance, and high security guarantees. But there's a trend that basically the more security options you add to an allocator, the slower it performs or the more memory it uses.
Cool. So we just discussed some of the key challenges that come in building an allocator. So this includes performance issues around CPU time, around memory utilization, multi-core challenges, security challenges, etc. Let's dive a little bit deeper into the sort of common design patterns of allocators today. And once we have sort of a deeper understanding of those design patterns, let's look at anti-patterns that are quite common in the real world. So one key design principle of most general purpose memory allocators is they will have different code paths for different sizes of allocations. And this is rooted in these three common assumptions. One, larger allocations are less frequent and have a longer lifespan. Small objects are more frequent and have a shorter lifespan. And objects of the same size are usually allocated and destroyed together. The third point actually is an assumption that a subset of the popular allocators today make. The first two are pretty much universal. And let's see what this means in the real world. We have a stupid little program here where we time how long it takes to malloc and free different size allocations. In this case, I'm using JMalloc master as of last Friday, but this same principle will apply to tcmalloc, glibc. The glibc will just be like 2 steps. And you can see basically here in JMalloc, and if I scale this further, you'll actually see like 4 step functions. So there's a specialized code path for smaller allocations, a different code path for normal large allocations, a different one for huge allocations. And that's something that you should consider when you are allocating and deallocating memory. A common mistake people make is they will have frequent large allocations with short lifespans. So these are expensive to allocate because they do require an expensive syscall to request memory from your operating system. So most allocators will have some threshold which once exceeded in terms of the size of the allocation will go straight to your operating system kernel to request more memory. They also involve slower data structures that are typically global, which has implications on multi-threading as well, which we'll get into later. And ultimately, it is just more memory. Someone has to zero it, and there's a cost to that, and it does end up thrashing your cache as well. It's expensive to free for many of the same reasons. So an interesting thing here is on multi-core, doing that unmap becomes excessively more expensive. And there is also a fast path to go straight to the operating system to deallocate that memory. In addition to that, for some allocators, particularly in Unix land allocators that are relying for sbreak, even for primarily for smaller allocations, generally there's a threshold there. It can be a major contributor to fragmentation. Here is an example of what that fragmentation could look like. So this is an allocator. This is a state of the heap. You have 3 8-byte blocks here, which are currently unavailable, a meg block, and then another 8-byte block. Someone calls free. Let's say we decide to, in some sequence of frees, the allocator decides to coalesce these free blocks. So coalescing and splitting are the main ways an allocator will help manage fragmentation. They'll coalesce and split free blocks. So it decides to coalesce these 3 8-byte blocks into 24 blocks, and then we malloc 32. In this situation, it would be forced to split. Splitting typically is more expensive than just a single step. There is a cost of coalescing and splitting. So in this situation, the allocator either has to pay the cost of coalescing and splitting, or it will have to allocate more memory. This can end up creating large holes. The other challenge with allocators that are using sbreak is basically the heap only grows and can only trim and allow the operating system to reclaim memory in the top region of the heap. So what can you do about it? One, don't do it. The other option is use a custom allocator, and we'll talk about situations situations where a custom allocator does make sense, as well as situations where it doesn't make sense. Some memory allocators will have tunables in there, so you could alleviate some of the side effects. So in the case of glibc malloc, so the default malloc on most Linuxes, you have the mmap threshold malloc, which specifies when it should use mmap over sbreak. The benefit of using mmap is it could unmap just that specific mapping, and you're less likely to have fragmentation. You also have a trim limit for the top of the heap, which you could tune. And then last but not least, some allocators, if you can afford the memory, you can also increase the threshold for when allocations are cached. Another common anti-pattern that we see, and some of you may be familiar with this, we'll go into the details why, is I see this quite a bit where people will malloc memory and then memset it, and they're like, oh, you know, the cost is, it's cheap, it's just the cost of freeing that memory, of writing that memory, we're gonna write it anyways, etc. You can see the time to execute here with this malloc memset, and calloc is pretty massive. And the reason for that, in particular for large allocations, is most things are demand page. So you always want to use calloc. So for example, your operating system will have something called a zero page, which is just a physical page of memory filled with zeros, right? It'll allocate a set of virtual VMAs for you, virtual address pages, and only when you write to that page will it actually allocate a physical page of memory for you. So that means you could, malloc 10 million, and it won't actually allocate the physical memory for you until you write to that memory. And this is actually why you have this big disparity between the two. This also applies to small allocations as well. Not all allocators will take advantage of this, but for example, macOS will not necessarily zero freshly allocated memory, and there is a performance differential associated with that. Cool. So the other thing I wanted to introduce, sort of a key design concept in a lot of allocators today, is the notion of a segregated free list. So common assumption all of them will make is small objects are more frequent and have a shorter lifespan. So generally speaking, there's going to be a code path that is optimized for these objects. So typically you'll have a cache either at the thread level or something at the arena level or heap level, depending on your allocator, which is used to fulfill all incoming allocation requests. And so you'll have some kind of cache of the recently freed blocks, and memory allocations will be fulfilled from there when possible. The challenge there, though, is determining which free block to use, and there are many strategies to this. Generally speaking, one of the best strategies is to have something that's best fit and address ordered. What that means is, for example, let's say I wanted to allocate I had an incoming allocation for 16 bytes of memory. We walked through this list, right? And we'd be walking through in linear time. We could use this 32-byte block, but then you have a lot of internal fragmentation, right? You're wasting 16 bytes of memory. So a naive implementation would either have to walk through this full list to find the best fit, or would have to use expensive index data structures that have high constant times to be able to actually fulfill the lookup. So what a lot of allocators do is they will use what's called a segregated free list. So pretty much every modern allocator today that is thread friendly will have some notion of a segregated free list, at least at the thread cache level. And basically what this means, this is a great approximation for sorted best fit. And what this means is, allocation will typically get rounded to the smallest size class that fits the requested size, and then that relevant list is scanned. So the other interesting thing here is, which is quite obvious, is some allocators will actually utilize this on the allocation path as well, which I'll get into shortly. But typically, if you're allocating 7 bytes of memory, your allocator will typically round that up to a size class or some alignment. So in the case of glibc, for example, it'll make sure that everything is aligned at a boundary. And you could see for smaller allocations, pretty much the smallest allocation size you'll get is 24 bytes. And that's a side effect of internal linkages, which Hannes referred to earlier for how chunks, blocks of memory are managed within within ptmalloc. With something like jmalloc or tcmalloc, they will actually apply the segregation for allocations and storage selection as well. And so having knowledge of these size classes is even more important. So in the case of ptmalloc, it just means that you won't be able to properly utilize a segregated free list. In the case of jmalloc, this will manifest as a lot of internal fragmentation. This is a pretty pessimistic example because I'm making allocation requests that are multiples of a size of 3. Right. So let me jump into the notion of slab allocation. So I mentioned that some allocators today will make the assumption that objects of the same size are usually allocated, accessed, and destroyed together. In other words, you might have a linked list of type n. You're going to be iterating over that linked list of type n. There's a lot of localities, so it makes sense to allocate them together. Generally, there are 2 basic schemes that you'll find in allocators today. This is a gross simplification. One is a slab-like scheme, so tcmalloc, jmalloc work this way. The macOS allocator will have an optimization for tiny allocation sizes, which is similar. And essentially, it'll pre-initialize pages for the same allocation size. So let's say you have a new 16-byte allocation coming in. It would initialize a new 4 kilobyte page of memory for 256 16-byte blocks. Schemes, glibc will use something that's closer to a bump pointer scheme, so it'll allocate new blocks from the current page on a first come, first served basis. This can have drastic implications on the performance of your application, especially if it iterates on dynamically allocated data structures. So there are a few simple patterns you can follow to avoid this. Let's look at a simple example. I have a high performance key value store called DongoDB. And the backing data structure of DongoDB is a giant linked list. So this is a linked list of 16 million nodes, which contains 2 fixed length allocations. The key is 34 bytes and the value is 64 bytes. And we just want to iterate on the key in this situation. And you can see there's a huge disparity between glibc and jmalloc and tcmalloc. Jmalloc and tcmalloc generally will have very similar performance profiles. Jmalloc is better about purging memory. So the reason for this is the fact that the bump pointer scheme will place allocations contiguously, while the slab scheme will place allocations contiguously by size class. And in this situation, we have a 32-byte allocation, a 64-byte allocation, and then another 32-byte allocation for the actual linkage to node. And so you'll end up with a memory layout that looks like this. So on most modern hardware that we hear about today, you're looking at 64-byte cache lines. And basically what this means is for the glibc implementation, you're looking at a node every 2 cache lines with the values you care about, while in something like jmalloc, tcmalloc, etc., you have 2 nodes per cache line and sort of a word and a half. You could preload some memory of the next word. So you have a lot more data density and it's a lot more memory friendly. Of course, there is a pathological case for slab 0 if you're using a lot of variable length allocations in your data structures. You can end up really thrashing your TLB, right? Because everything is fragmented across so many size classes. So key takeaway here is factor access patterns in your allocation sequences, especially for read mostly data. Generally try to couple allocations close to where they'll be accessed. Variable length allocations can be pessimistic. A common mistake people make is they just assume, oh, fewer mallocs is better for performance. That's not the case with allocators like jmalloc, tcmalloc. If you end up having everything spread across a lot of size classes, that will be bad for your TLB. The fundamental reality, though, is if you really, really want to optimize this down to you want to squeeze every cycle out, the malloc interface itself is inherently limited in its ability to express relationships between allocations. So there are alternative interfaces that attempt to address this, but basically they all have significant limitations. Some cool work that Alexandra Fedorova did at Fraser University is providing an allocator interface that allows programmers to specify the relationships between different allocations. And one thing they were looking at is utilizing PMCs to automatically extract spatial locality. I think one thing that would be very cool, is for Fedorova and Emery Berger to talk. It would be awesome to see the techniques in Mesh applied to some of the work that she's doing for performance. All right, the other thing I want to talk about briefly was growing a region of memory. So most of us get it wrong, but some people do get it right. FB vector is a perfect example of a data structure that does get growing memory correct. So, one mistake obviously is just growing by 2 has implications, but one of the key sort of secrets to FB vector is it is aware of the underlying allocator. So it'll make sure that the capacity is always rounded to allocator size classes, so blocks are fully utilized. You don't have this internal fragmentation, and it uses allocator extensions to grow in place. And you can use these extensions yourself as well. So tcmalloc has a few of these, jmalloc has a few of these. Unfortunately, glibc does not have anything here. So in jmalloc, you have nallocx, which given the size of an allocation, it'll return back to you how much memory it would actually allocate for that size, right? The other thing it gives you is an alternative to realloc, which allows you to basically realloc in place. So let's say a size class over there is 48, and you do a realloc from 40 to 48. It can probably grow in place, and it'll just return. There are other optimizations that can also apply. So just use nallocx to round up to your allocation size class, and then xallocx to attempt in-place resize. And this is great for performance. There's going to be a whole bunch of other useful extensions you haven't heard of as well, so check out your allocator documentation. One of the downsides of the malloc interface is it's not good for performance. Every time you do a free, your allocator has to look up all these data structures to determine the size of the allocation that it's freeing in at least some of the allocators. This can be fairly expensive. So jmalloc has an interface where you could pass in the size of the allocation to avoid that lookup. In C++, generally speaking, you're going to know the size of the underlying types. And this is, again, a very cheap optimization you can apply to improve performance. So check out your docs. All right, so a lot of what I talked about touched on fragmentation. I wanted to just briefly talk about how you can detect fragmentation. Generally, what this will look like is your allocator will request more and more and more memory from your operating system. Not all of it may be resident. Generally, it won't be. Here's an example of fragmentation in the real world from some application. So it'll look something like this. jmalloc helped improve the situation drastically for this workload. How can you measure fragmentation? So a lot of allocators today will have allocator statistics interfaces. The ones I touched on, glibc, ptmalloc, jmalloc, tcmalloc, etc., will expose this. The macOS allocator. glibc has malloc info, jmalloc has malloc stats print. And in the case of malloc stats print, it'll give you a whole bunch of stuff, and it'll also give you how many pages were actually allocated and how many of those pages are in use. So you can just take the ratio of these to approximate external fragmentation, and it's a pretty decent measure of that. So this is what fragmentation looked like for the backtrace debugger running on Firefox. Internal fragmentation is more difficult to measure, but it can be quite substantial. So the only options I know of today are wrapping or allocations, which is pretty coarse-grained, or dot from Valgrind. So over here, run dot on backtrace, the backtrace debugger again, and dot tells us this particular allocation in this function. Each byte is written to 1.2 times, each byte in the blocks are written to 1.2 times on average and read from 0.41 times on average. This is saying that we are allocating a lot of memory and not using most of it, not reading most of it, and there's probably more digging to do. Common sources of internal fragmentation that we've seen in the workloads we've dealt with are dynamically growing buffers that are not resized to fit. So a lot of container structures will have shrink to fit. Call that if you do have a static structure. Other thing is just internal padding and alignment. So if you're on a platform that emits dwarf, check out the PA hole tool, and it'll tell you about any blocks of memory that are being wasted for alignment or padding. So in this particular structure, for example, there's a 2-byte hole that's not being utilized for anything, any useful data due to alignment. So rejiggering the data structures helps with that. General rule of thumb here is try to order larger fields first in your structures. and also consider the access patterns of those fields as well. All right, so on the topic of fragmentation, I'll hand it off to Paul to talk about how we can make fragmentation worse.
Thank you. All right. I've already mentioned the TLB a couple of times. The TLB is this cache that lets hardware translate virtual addresses to physical addresses more quickly. And the thing you notice when you look at current chips is that the size of your level 1 TLB, the fastest level of that cache, can cover, in the best case, roughly about the same amount of memory as your level 2 data cache. So if you have, like, say, a large hash table that is bigger than 256K, like much bigger than your level 2 cache, when you try to read into it, find your data, sure, you'll have to pay, like, L2 cache misses, probably go to memory, but you will also have to pay for memory translation. And that can often be almost as slow as servicing the cache miss itself. So what do you do about it? Well, we could use larger pages. That way, you have the same number of entries in your cache, but each entry covers more data, and you're happier. The problem with that is that huge pages are extremely easy to misuse. One very well-known case is Redis that uses the JMalloc allocator, and if you're not careful with it and you enable transparent huge pages, all of its allocation will be backed by huge pages. Then it forks, tries to serialize its heap, and everything goes to hell. So in this post, it shows how to disable transparent huge pages. You can also use the same interface to enable transparent huge pages on Linux. But I don't think this is the right way to do it. Like, you probably don't want to enable transparent huge pages for everything on your system because, again, when they fail really hard. So instead, what we should be doing is use dedicated hooks in our memory allocators. So if you use libcmalloc, you can use libhuge-tlbfs to enable large page backing data. You have similar hooks for tcmalloc and for jemalloc. So you have to be careful. This is really far from free. Probably want to talk to the system administrating people because the best way to use huge pages is to pre-allocate them at boot time to make sure that you don't have later fragmentation that prevents your application from getting the free pages it expects. And you're also going to pay with external fragmentation, which makes sense, right? If you have, say, one 4 kilobyte page, it has to be kept in memory because of one 10-byte allocation, or you're wasting 4K. If it's the same thing for a 2 meg page, well, now you're wasting 2 megabytes of data, and that hurts a lot more. Okay. We've already mentioned that the multi-core evolution created new scaling problems for memory allocators. Here's a new one that is very common. I don't know if it has a good name, so I just stole this term that the HFT people use. It's called the allocator bleed. And it's essentially what happens when you have a producer-consumer pattern where the producer uses heap allocation to create the work units, passes them, say, with like a ring buffer to a worker, the consumer does its work, and then frees that work unit. So what's going to happen with libcmalloc, right? You have the allocator, calls malloc, gets its work unit, dispatches it to, in my case, a 32-entry single producer, single consumer ring buffer. It goes to the worker does nothing because it's a micro benchmark, then immediately calls free. How fast can we do this kind of loop? Turns out it takes 1.4 microsecond per item to go through this process. And if we look at the stats, we can't even fully utilize our 2 threads. Like, what's going on here? So here's one way to fix this. We could simply send the work unit back to the producer on a separate ring buffer, and then the producer can free it itself. And now we get 3 exit throughput and actually the scaling that we expect from the number of threads. The reason this happens is that when we free in the wrong thread, we end up using the operating system as a queue to transfer these resources back to the producer thread. And that's going to be slow, much slower than a lock-free ring buffer. And it can also happen, let's say, with jemalloc, which uses the same workflow, but instead of going through the operating system, uses its own internal locked data structures. So what can we do about it? The first one is that it's not always obvious when it happens. I don't have a very good way to pinpoint these issues, but one thing we can do is just look at the thread cache statistics for all these worker threads. And if we notice that there's like a lot of allocation that are in the thread cache for a size that the worker doesn't really use, this might be the reason for filling the thread cache with useless information. Once we do know that it's a problem, what can we do to fix it? Like I said, we could use an explicit release queue and send the allocation back to the producer so that the producer can free it and recycle the allocation itself. However, that's a bit error prone and that's a lot more overhead to the coder. So I like to simply, a lot of times, the worker will already have a notification back to the producer to say, hey, I'm done with this work. So we can take it back on that and send the allocation back to the producer. Finally, the best thing to do is simply not do it, right? Just don't transfer ownership. Like if you use gRPC, the request is passed in as a const reference. So you know that the caller just always maintains ownership of the original request. All right. Something else that happens with thread. We already mentioned that in order to alleviate contention with multiple threading, we use arenas. So that's a lot of kind of private subheaps, and we assign a ton of threads to them. The problem here is that each of these arenas will have their own allocation cache. They will have their own resources. And since it's very slow to transfer resources from one arena to the other, they tend to just hang on to their allocation. So if you have a ton of threads that go in one arena, do allocations, and then go to sleep, for instance, because there's no more work to do for a while, or because they're all waiting for disk IO, these allocations that were freed will just remain in the thread caches or in the arenas, will not be available for reuse anywhere else. And that needlessly increases the size of your process. So if we want to avoid that, we would like to avoid the out-of-memory killer. So what can you do about it? Well, maybe try to use fewer threads. That way you'll have fewer arenas and less wasted resources, but that's not always an option. So some allocators like JMalloc and TCmalloc that are geared towards server workloads will have explicit ways to turn off the heap for these threads and say, mark them as idle, please reclaim these resources. And they will also have ways to enable background cleanup threads that can go around and figure out that data isn't being used, so it's okay to free it and release it to other threads. And yeah, if you're on Linux, there's some work to try to address that with restartable sequences. That's a nice way to get per CPU data structures in user space, but I don't know of any open source malloc implementation that currently implement that.
In recent times, we see lots of trends of computers getting more complex. And so it appears that also our like single memory to CPU mapping is not up to date anymore. We can see this in the high-end server space where we have multiple sockets and multiple sockets connecting to each other over like certain types of links, which form some kind of topologic structures over which they can communicate memory. But also like, for example, trends in mobile phones where people try to conserve power. And one way, for example, could be like actually to turn down certain memory chips and power them up only when needed and get the memory back from more stable storage. So what this means is like, even like if we have like a pointer and that addresses memory, we don't know if this memory is like actually faster or slower to speak to. And one reason why we mentioned this in this memory allocation talk is especially because not a lot of memory allocators actually have a notion of non-uniformity in memory or like in access latency and bandwidth to memory. Some are oblivious to this because like their internal algorithm kind of like lends automatically to try to keep data local, but this doesn't need to be the case for lots of allocators. So if you are in the bad situation that, for example, your memory allocator, or that you are, for example, allocating your first piece of data on one particular NUMA node, this malloc will probably also generate like the additional metadata along with it and will automatically bind it to this NUMA node. But maybe this is just like the dispatch core, which actually will just send all other work to other cores and will thus distribute like the memory allocation load on them. On Linux, the default is if you basically just do a memory allocation with mmap, which is being used by malloc, you basically bind your memory to, or it tries to allocate from the local node and doesn't try to reach out to other nodes. And this is not being easy you can't really overwrite it very easily. there is some progress in like trying to measure like when memory can actually follow threads around, but it's not the normal case. So this is kind of like needs a lot of involvement in terms of how you program, because you might need to actually use like lower level libraries to actually extract your thread affinities, for example, and bind your threads and memory to certain cores. So basically, it's the same picture what you see here. You need to like be aware of how you're mapping between like your memory and your threads are. And we will see later on when Paul discusses it, how to, for example, use arenas manually to actually build up a mapping to allow for more fine granular memory management here. Another thing we see with operating system is that memory allocators don't actually care about like the boundaries the operating system is working on, if it's like pages or even like huge pages. It just like takes whatever is available. And if you actually rely, for example, on particular artifacts of like heuristics of your operating system, trying to estimate like certain patterns your application is doing to the memory correctly, you might actually want to end up to allocate your pages on page boundaries, which is like the smallest granularity the operating system can handle. And we will prefer to use like POSIX memAlign or standard aligned alloc, which basically like goes into the memory allocation and tries to do some better job instead of manually trying to align the memory along with it. So one example is in glibc malloc, ptmalloc, is that it actually splits up the allocation. So whatever you have as cutoff, for example, at the header to actually align your allocation to a page size, this will become a non-allocated, a free chunk, which can be allocated later on by a small allocation if it's being satisfied. So we recommend this pattern. Again, like for example, in some memory allocators, like for example, also glibc, you have the problem that metadata needs to be like aligned before the page. So in this case, even like if you have a page alignment, you actually have metadata before the page. So there will be an additional page right before your allocation additionally. Another thing where memory allocators and operating systems kind of conflict is like overcommit. I try to speed up here a little bit to actually get the other slides. The question is like, when does an operating system actually allow you to allocate memory? Because sometimes the operating system knows, okay, no further memories are available, or it can actually like say, okay, I doubt that actually the application will handle or will actually use all memory which the application asks for. We say an operating system overcommits if it allows you to allocate way more memory than the operating system is actually able to store in memory or in physical memory or in swap. Linux has a tradition of basically doing that for a long time, FreeBSD as well. I think I heard Solaris isn't doing this, as well as Windows. So basically this dictates how you need to be careful with your memory allocations. If overcommit is enabled on your operating system, you can basically, depending on like how strict it is, most of your allocation requests will be fulfilled and you will actually get an allocation back. On Windows or Solaris, for example, where you don't have memory overcommit, you actually need to check your malloc return values for null and act accordingly. There are also, so there are lots of people who actually say like, okay, so Linux basically was there's a lot of overcommit, which uses a lot of overcommitting. You don't actually need to check for null pointers, but there are also like different memory allocators in play between you actually receive the memory from your allocator. And this is, for example, one example where Linux would probably just allowed you to give you the memory, but in the end, your malloc implementation had a limit which didn't allow you to go any further, and so you got a null back. If you get a null back, there's sometimes nothing you can do, and you should probably crash accordingly and print a proper like log message. In other cases, like try to clear caches that you have, for example, in your application. Try to free whatever you can. There are, for example, ways to ask jemalloc to purge particular arenas. So it frees actually memory up and gives it back to the operating system. And other ways you can use for certain allocators to try to push data back to, or like to free memory back to the operating system. Okay, in case of security, as I initially said, like it's difficult for allocators to be like really secure and to also be fast. So there's like a problem on how far they can protect you. There are actually only a few things you should probably take along with you. So first of all, it's like if you have actually crashes and if you have problems with your application using your memory allocator, it probably doesn't crash at the site where the actual bug is. This is because of like delayed metadata validation, for example. If you think about like if you walk a linked list and you check actually every element, it depends on when the element is actually being inserted and when a particular data structure of your metadata is being overwritten, when the actual detection from the malloc implementation will, for example, abort your program in this case. It's also like necessary to say that a lot of those memory debugging libraries, which lots of people think they should run in production because they abort the program way earlier before, if I don't run them, they actually also add gadgets to your program, which can be exploited by attackers. So there have been in the past attacks using address sanitizer, for example, on production systems. And I would still not recommend running them in production. The same is, for example, that for example, malloc is also warning against, like, for example, running malloc check in production systems, especially like if you are like in a security restricted area. Okay. Yeah, so debugging has like this problem of trying to balance between like, or making like your life easier between validating whatever you do on your heap and the state you are in at that moment. So for a proper debugger, for example, if you look at address sanitizer, you add a lot of additional metadata and a lot of like synchronization overhead to actually make sure that nothing ever like is being missed from your allocation pattern when there should actually be an error. I just quickly go over the debugging features. So whatever you can do with debugging in memory allocators is basically, lots of debuggers nowadays allow you to dump your heap state when you have a mini dump or a core dump. Then you basically always can look in the manuals of your memory allocators that you will find some other features that enable stricter checks, whatever, at the time when you do mallocs or frees and will validate the metadata more strictly. You can use, like, for example, operating system provided tracers that allow you to follow malloc or freeze along with the application and very good timestamps to hopefully order them in correct time and then see, for example, how pointers are being created and being returned to your application and then being freed again. You have certain malloc options which you can enable hopefully during runtime. Some malloc libraries require you to actually recompile your application. You can use, for example, like more heavyweight machinery like Vagrant, which is kind of like a virtual machine monitor that sits between your app and your app and the operating system and just like tries to look everything what goes in and out and every pointer and read and write access from your pointers and looks at which allocator problems you might have or which pointer accesses you got wrong. And then you have like two toolchain integration, which basically are the sanitizers that work between the compiler and libraries and allow you to figure out with higher performance what your problems are, but they actually require you to recompile your application and maybe even like your dependencies. So integration of them is a little bit more troublesome than some other alternatives.
All right. I will also quickly mention you can run a GWP ASAN, which does not stand for Google-wide profiling ASAN. It was upstream in Khuong, and it runs pretty well in prod. Look it up. All right. So we've done all this discussions about how it's hard to do a general purpose memory allocator and how you have to work around your weaknesses. So I think a natural question is, why don't we just write our own custom memory allocation? Right? We know what our app looks like. We should be able to fit to it. Turns out that's very hard. So this paper came out in 2002, considering custom memory allocation. They compared a bunch of industry programs with custom memory allocators, and they said, let's just remove that, use standard DL malloc, and see if it's a win. Turns out, it's almost never a win to write your own memory allocator. So don't do it, and if you do it, make sure to measure your baseline because it might be a lot better than you expect. However, let's close with if you think this is actually a good idea. You really know what you're doing. So here's one thing that's useful. It's sometimes you want to control the placement of your memory. Let's say you want to use persistent RAM, or you want to make sure that large hash tables are backed by gigantic 1 gig pages. What do you do with that? Well, different memory allocators offer you hooks to only replace the way that they interact with the with the operating system to get more bytes. Nothing else. So you don't have to worry about all the algorithmic of memory allocation. However, this is most useful when targeted for specific allocation. And apart from JE-malloc, I don't know which ones let you just override for one type of allocation. With JE-malloc, you can override for a given arena and then target the arena explicitly for these special allocations. Then there's the object pool, which is mostly useful if you can avoid the construction and destruction overhead, right? However, sometimes it still makes sense, for instance, if you need a stable allocation, it's because you want type stable allocation because you're doing log-free programming and someone might temporarily read a still pointer only to figure out later that that data isn't useful. If you do that with a standard memory allocator, at some point, the byte might become something else and you're just gonna start doing weird stuff in your code. It also makes sense for some interesting edge cases, like the one we pointed out earlier. We have frequent short-lived large allocations, and maybe you want to use an object pool for that. And the nice bit here is that you don't have to write your own. You can use Boost, you can use the one in, you can use standard lib C++. But also, like it's not that hard to write your own. Might make sense to specialize on your specific requirements if you're going to do that, because you really want to make sure that you have as little overhead compared to the regular malloc interface. And finally, the one exception from that paper by Emery Berger and others in 2002 was region allocators. They found that region allocators were the only one form of custom allocators that were useful. They did offer increased performance at the expense of a much higher memory footprint. All right, so how does a region allocation work? You grab a large chunk of memory, contiguous, and then for every allocation, you just increment a bump pointer, and free is a NOA. Until at the very end, you say, well, everything that was allocated in this region is good to go, and that's when you freed your chunks. So to implement that, well, you could use a CD scoped allocator adapter or polymorphic allocators, but I find that the state footprint, simply to know if you enabled or disabled arena allocation for this specific object, and the virtual calls add up. So what I've been doing is we use a region per thread, and you have a thread local flag instead of a bool in each allocation. And that flag says at allocation time, do you want to use the regular allocator or do you want to use a region allocator? And then when it comes to deallocation, you don't know, right? You can't just read data. So what I did is I have a metadata bitmap, say I know my chunks are 2 megs and they're aligned on 2 meg boundaries, then I can just have a bitmap that tells me for each 2 meg range of memory, if that memory is managed by malloc or by some other system allocator, or if it's managed by my region system, and then the deallocation should do nothing at all. All right, and this is more tentative. If you have a mix of short-lived and long-lived allocation, try to treat them differently. ScyllaDB does that with its log structured allocator, and they found it was very good for performance and fragmentation. You could also try to do the same thing by specifying the arena you want to use in JE-malloc. All right, do you want to close?
Thank you. Just want to point out a few other talks that are interesting on the subject. So Paul and I will be talking about cool lock-free data structures that always perform better than their locked equivalent, or in even some cases serial equivalent. There's a talk Wednesday on TC-malloc internals, which will be go into a lot more detail into the design and implementation of TC-malloc. And then, of course, there's a mesh talk. These are our emails and Twitters, and we'll just open it up for questions.
You get an icebreaker from your staff.
Huh?
You didn't get an icebreaker from your staff?
Yeah.
Hey, I actually have a question.
Yeah.
Woo.
Your talk has a lot of malloc and freeze. I tried to use make unique and vector.resize. How does that translate? For example, for like avoid malloc and use calloc, that kind of thing. Like is the C++ library able to see through my allocation and say, okay, this amount to basically 0 alloc thing through your constructor, so it's just gonna do the right thing. How does that? Do you observe anything like that?
Okay, so there are two questions here. One is, given the standard C++ allocation interface, how does that relate to malloc and free? So it turns out that usually your allocate and deallocate calls in the standard allocator will eventually go to regular malloc and free. So all these things we said about making sure that your lifetimes are correct, this still applies in C++, right? The other one was, do we know of any C++ allocator or container that we know to use calloc to make zero failing faster? I don't think it would be a very good idea, but also it seems very hard to guarantee with by compile time reflection that this is what you want from the default constructor.
Thank you.
Cool. All right. If anyone wants to chat with us, we'll be at the Backtrace booth outside.